So, what would happen if you wanted to come up with the 10th term? Well, to come up with the 10th term, you would need the 9th term, which would require you to have the 8th term, which would require you to have the 7th term, which of course needs the 6th term, which of course has to have the 5th term, which now would require the 4th term. But that one you have, so you would have negative 11. And then you would, well, continue on that process all the way forward until you got to negative 41, which is the 10th term. So if you needed the 50th term, which is in this case n equals 50, this is not going to be very efficient at all because you have recursive process requires the 50th to have the 49th term, which requires the 40th term, and so on. And so we're going to need to do it a different way. We're going to need what is called an explicit formula, which allows you to find any nth term without having actually to generate the prior term to get to that point. I've added the explicit formulas to the arithmetic and geometric sequence table. Looking at the arithmetic explicit formula, a sub n shares the same rule as a sub n in the recursive formula, which is to find the nth term. A sub 1 also is shared the same way, meaning to find the first term. We'll even say the same thing about the common difference d. Now, the main difference between the two formulas is how the n minus 1 is treated. Here, it's a subscript, which just means prior term. Over here, you're taking this quantity of n minus 1 and multiplying it by d. Why does that actually happen? If we look at the sequence of 2, 5, 8, 11, and 14, and we wanted to figure out this term, which is when n is equal to 5, you first realize that you would be adding 3, the common difference, to the terms. But how many common differences did you actually add? Did you add 5? I don't see that. I see 1, 2, 3, 4. It actually takes one less of the 5, so in this case 5 minus 1, which ends up being 4, and you actually added that many common differences throughout the process. And that's why we would add 12 to get to the 2 to get to the 14. And so an explicit formula will always require one less the value of n being multiplied to the common difference to get to that term immediately. And we can just go from here to here instantaneously. If we look at the geometric sequence formula for explicitly, again, they share the same rules. G sub n to find the nth term, G sub 1s to find the first term, the R defines the common ratio, and again, n minus 1 as an exponent is telling you that you're going to multiply by the common ratio over and over again, as many times as n minus 1, where this just means prior term. Going back to our original arithmetic sequence of 2, 5, 8, 11, let's write its explicit formula. And the explicit formula for an arithmetic sequence is a sub n equals a sub 1 plus the quantity n minus 1, which is then multiplied by d. We fill in the first term where a sub 1 is. We fill in the common difference where d is. But what we do not do is we do not fill in the n in the formula. And the reason for that is at some point I will want to figure out what the 50th term is, I will want to figure out the 100th term, and I'll need to put in that value of n at that time, but not now. So if we look at the formula, the first term being 2 and the common difference being 3, I could write the formula is a sub n equals 2 plus the quantity n minus 1 times 3. Now, if I wanted to find, let's say, the 20th term, I'm now establishing that n is 20. So now I am filling in the n into those spots. But I only wanted to fill in the n now. And so a sub 20 will equal the first term 2 plus the fact that I'm going to go and add 19 different values of 3 to that 2, and I'll be able to come up with 59. We could take that arithmetic explicit formula we just wrote, 2 plus the quantity n minus 1 times 3, distribute to 3, and then combine like terms to come up with an equivalent equation of a sub n equals 3n minus 1. And if you're following along with my note sheet, then I would add this to the page 2 of the notes. What's most important is to understand that arithmetic sequences are linear based. And that is something that, again, if you're using my notes, I would add to page 1. If we were writing the explicit formula for the sequence 3, 6, 12, 24, 48, we would need to remember that the geometric sequence explicit formula is g sub n equals g sub 1 times r raised to the n minus 1. Now fill in g sub 1 with its first term. Fill in r with the common ratio. Do not fill in n in the formula. So taking the first term, which is 3, and taking the common ratio, which is 2, I'd be able to rewrite the formula as 3 times 2 raised to the n minus 1. And if I wanted to find the 30th term, now is the time you take the value of n and you plug it into those spots right there. And you would say 3 times 2 to the 29th, which works out to be 1,610,612,736. Looking back at the geometric sequence's explicit formula, g sub n equals 3 times 2 raised to the n minus 1, it reminds you of an exponential function, where the a initial value is the same as the first term, where b, your base, happens to be the same as the common ratio. And the exponent, x, takes on the same role as n minus 1 does up here. And that's why geometric sequences are exponentially based. Returning to the recursive formula where t sub 1 equaled 4 and t sub n equals t sub n minus 1 minus 5, you might recall I wanted you to find the 50th term, which would then require you to do the 49th, 48th, and so on. But actually, we'll rewrite this as an arithmetic explicit formula because we saw that to be 4, negative 1, negative 6. So fill in the first term, which is 4, add the quantity n minus 1 times the common difference being negative 5, and you can then find the 50th term by literally plugging in 50 into the values of n, and you'll come up with a value of negative 241, significantly faster than going through the recursive process.